Hello, this is Matt Roscoe at the University of Montana with the replacement lecture for my absence for our course M234, Math for Elementary School Teachers, Higher Math for Elementary School Teachers. So the first thing I want to do is show you where you can find material for this lecture. So we're on the section. We're going to just do the first chapter of our number theory chapter that's coming up next. So if you'll go to number theory, you'll see the slides here, and then there are a couple forums, and I'll talk about that once I'm into the lecture. So here we are on factors and multiple. I'll go start the presentation. And so chapter 8 is all on number theory, so things like factors, multiples, evens, odds, primes, composites, as well as tests of divisibility are all in there. These are things that we teach children in grades kindergarten through 8th grade mathematics. So let's start by just talking about factors and multiples today. I do want to call your attention to the fact that this one will not, this chapter is not on the upcoming test on Wednesday, and we're just using it as a way to delay the test a day so that I can get back and review and be with you during the testing setting. So opening question, then I want to define what a factor and multiple is, and then we want to talk about a methodology for finding all the factors of a number, and then ask the question, do factors always come in pairs? So here's the opening question. Elsie has 24 square tiles that she wants to arrange in the shape of a rectangle in such a way that the rectangle is completely filled with tiles and every tile is part of a rectangle. What are the different rectangles that Elsie can make, and what did they tell you about the factors of 24? So go ahead and take some time to do this. I might suggest that there is a nice website that you could use. It's found at the mathlearningcenter.org. Apps and patterns. If you go to mathlearningcenter.org, there is these apps, and there are things for pattern shapes there. I'll go ahead and open it up and show you the web app for pattern shapes. It just looks like this. These are the common pattern blocks we see, often used in mathematics classrooms, and you can put a square grid down and pull these things to the grid. There is some nice the ability to make these things. You can highlight them and edit them, so you can change the color if you'd like, for example. But that's the idea. I'm going to start out with small ones, and then once you have one highlighted, you can actually duplicate them. So I could get two there, and if you want to duplicate two of them, you can draw a circle around them. It highlights both, and you can duplicate both. So you might play around with this website to get a sense of, well, if I have 24 tiles, what are the different rectangles I can make? So why don't I just stop there and ask you to pause the video and come up with either a drawing or go to this website and see how many different ways you can arrange 24 tiles in such a way that the shape that they make is a rectangle. Okay, so hopefully you've paused and had some time to think about that and you have an answer. I have my answer here on the next slide, and this is what I got. When I sat down to do it, I found that you could arrange them in a 6x4 rectangle, or an 8x3 rectangle, a 12x2 rectangle, or the one that often gets overlooked, the 24x1 rectangle. And of course, this is the activity that we often use to introduce students to what factors are. Each one of these numbers, 6, 4, 8, 3, 12, 2, 24, and 1, these are all the factors of 24. And in fact, finding factors of 24 is exactly the same thing as finding two numbers that, finding numbers that multiply together to make 24. Now, with the caveat that those numbers have to be whole numbers. And anytime that happens, of course, you can make a rectangular array out of those two numbers. So it turns out that 24 has exactly 8 factors. They are 1, 2, 3, 4, 6, 8, 12, and 24. One thing to notice is that for any number, we'll always have this representation, right? For any number, we will always have this representation. That's because every number can be written as 1 times itself. So we always get at least one rectangle. And then we get some others potentially. And so that's kind of interesting. You always get at least one rectangle and potentially some others. Okay, so let's go back to, um, so what about the, I guess thinking about other numbers in the same way. So let's just do it again. What if Elsie had started out with 25 tiles? How many rectangles could she make then? And how about 29 tiles? And what do these results tell us about factors? Okay, so let's take again some time. Um, Perhaps you want to go back again to your pattern shape website and spend some time playing around with 25 tiles and spend some time playing around with 29 tiles. So once again, I'll ask you to pause the video and ask yourself or investigate these two questions. You've got 25 tiles. How many rectangles can you make? And you have 29 tiles. And how many rectangles can you make there? So I'll ask you to pause now and investigate those two questions and then come back with answers prepared to I guess to see what I got. All right, so hopefully you had a chance to think about the question. Again, the idea here is that 25 tiles, how many rectangles can she make? 29 tiles, how many rectangles can she make? And what does this tell us about factors? So these are my answers for 24. Let's take a look at my answers for 25 and 29. Maybe I should draw these in a different color so we can distinguish them. Let's make those, I don't know, blue or something. There we go. So the 25 tiles in blue on top can be written in one of two ways. So you either get a 5 by 5 or 1 by 25. And the 29 tile, you can only write this in one way. It's 1 by 29. And so what is it that this is meant? I mean, why did Beckman, I guess, suggest that we go about this way? So for example, some numbers you can get 5 different arrangements. And in this particular case, each arrangement has a length and width which is different. And in some cases, you can only write them two ways. In this particular case, if you write them in two ways, it appears that the only two ways, it appears that this one is you can actually, I guess what this teaches me anyways, is that some of the rectangles you make happen to be actually squares, which we didn't see that before. Here we saw all true, I guess, non-square rectangles, whereas here we're seeing, with the 25 case, we see the square, the rectangle that is a square, actually. And then it's also possible that some numbers, like 29, can only be written in one way. So it looks like 1, 2 ways, 4 ways are different ways, different, I guess, possibilities when we write these things as make these numbers into rectangles. So I guess what it's trying to teach us is that sometimes you only get one possible rectangle. Sometimes you get two. Big question would be, is it possible to get 3? We don't know that yet. We can definitely get 4, but it seems like what we're learning is that different numbers have different combinations of displays when written as a rectangle or as a product of two numbers. And so what that kind of seems to say is that the size of the number, like 29, doesn't necessarily mean that it will have a lot of factors. Notice that 24 is actually smaller than 29, but it has many more factors. It has 8, whereas 29 only has 2 factors, 1 and 29. And so that's one thing to point out to kids, if you ever teach this, is that the number of factors doesn't necessarily depend on the size of the number. And in fact, these special numbers, I don't know, if I had you in front of me, I'd ask you, well, what are the special numbers that can only be written like these? And of course, that's a prime number, right? That's a number that has exactly 2 factors, one in itself, and any number that falls into this category is a very special number in number theory. It's what we call a prime number. So just some things I guess we can learn by looking at numbers when we think of them as rectangles. So I think we're ready now to really talk about, well, what is a factor? So, so here's the definition for factor. In general, on this column is sort of the definition, and here's the example, parallel example. So if A, B, and C are counting numbers, so these are whole numbers, positive whole numbers, and A is equal to B times C, then A is a multiple of B, A is a multiple of C, B is a factor of A, and C is a factor of A. These two numbers, or two terms, factor and multiple, are often confused by children, and it's something you'll fight for sure if you get to teach this. So for example, 36 equals 9 times 4. So from that equation, we can then apply the definition and say that 36 is a multiple of 9. It's also a multiple of 4. And that 9 is a factor of 36 and 4 is a factor of 36. Sometimes you see the term divisor used in the place of factor, and that's fine as well. So a factor is the same thing as a divisor if it helps you to think of it that way. All right, let's move on and talk about another example here. So it says Therese is looking for all the factors of 156, and so far Therese has divided 156 by all the counting numbers from 1 to 13, listing those numbers that do divide 156 and listing the corresponding quotients. So here's Therese's work so far: 1 and 156, and he has it written as 1 times 156. 2 and 78, 3 and 52, 4 and 39, 6 and 26. So he must have skipped over 5 because 5 did not divide it, right? And then he skips all the way from 6 to 12, and he gets 12 times 13 is 156. And in the next sentence, he has 13 comma 12, whereas 13 times 12 is 156. And the question is, should Therese keep checking to see if numbers larger than 13 divide 156, or can Therese stop dividing at this point? And if so, why? And what are all the factors of 156? So let's take some time to just sit and think about that a bit. I'll pause here for 10 or 15 seconds, and then we'll talk it over. All right, well, that was 20 seconds to think about it. If you'd like more time, go ahead and pause the video to think about it longer. But it does look like Therese can stop dividing at this point. And the reason is that he's gotten to this point where we can kind of see the thing turning around. So let's just sort of think about what's going on. I'm going to switch over to my Elmo cam and we'll talk about it a little bit. All right, so he has Therese as, oh, I need to push this down on the other page. There we go. Oh, didn't like me. For some reason it doesn't want to maximize on my screen here. So I'll do it this way. I wonder if it will. Nope, still goes to the other screen. Okay, so he has written 156 down, and so far he has 1 times 156. He has 2 times 78. He has 3 times 52. He's got 4 times 39. He skips 5 and he gets 6 times 26. And then he does 12 times 13 and 13 times 12. And the question is can he stop counting? And I hope it will make sense to you that if Therese keeps counting ways to multiply to get 156, that the next one he's going to get between 13, if he counts up by 13, is he's going to get 26 times 6. And the reason I know that is because, you know, traveling between 6 and 12, the quotient decreased between 26 and 13. Um, so in other words, as he searched the divisors 7, 8, 9, 10, and 11, he found none that evenly divided 156 until he got to 12 and the quotient was 13. So that means that there are no numbers between 26 and 13 that will divide it. Um, so that means that 26 will be the next one. And of course 39 would be the next one, and it would be times 4. And 52 would be the next one, and it would be times 3. And 78 would be the next one, and it would be times 2. And then 156 would be the next one, it would be times 1. So you can see that if you adopt this search strategy, there is some symmetry here. That means, you know, you're not gaining any new information if you carry out the strategy of just searching one side until you get to this sort of turnaround point. So I mean, I'll call it a line of symmetry of products. And I hope that you can see this, right? That we already know that 12 and 13 are factors of 156, so we don't need to know that again. And the big question is what is this turnaround point generally for a number? And I don't know if you're seeing it, but it's the spot, right, where the two factors of the number would be the same, right? We're getting close here. 12 and 13 are almost the same number, but in a sense, you know, where is that? That's where a number times itself equals 156, right? Well, we know how to do this because we've passed an algebra class before. That means it's x squared equals 156, and I know to undo a square, I square root, so a square root of x squared would equal the square root of 156, and the square root of a square, of course, is just x itself. And if I hit that on my calculator, then what would happen is I would get 156, square root of 156. I get something like 12.48. I'll call it around 12.5. So at 12.5, if I multiply 12.5 times itself, I get just about, let's see, 12.5 times 12.5. Yeah, just about 156. It's a little bit big because of the round off error. But that tells me that I need to search every number up to 12 to see if it's a factor, and it will provide me the other number, which will obviously be larger than the one I search, that will go along with it. And so that's sort of the idea. There's an efficient way to look for factors that involves searching every integer up to the square root of the number for a factor and its pair. So these guys would be the factors. There are, what are there? 1, 2, 3, 4, 5, 6. There are 12 factors of 156. They are, here, let's just write them down. 1, 2, 3, 4, 6, 12, and then 13, 26, 39, 52, 78, and 156. So that's the way that you can find the factors of a number fairly quickly using an efficient method. Let's try another one just as an example, and maybe you want to try it on your own and pause the computer right now or the video right now. Let's try something like 100 and let's try 86. Okay, 186. Let's try to find all the factors of 186 now. So first thing I'm going to do, if you want to pause, you certainly can, is I'm going to take a look at 186, take a look at the square root of 186, and see what happens. We get 13.6. So it turns out that we have to search every number 1 through 13. I'm going to just write them down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the big question is which ones divide 186. So let's see. Certainly 1 will. It's 1 times 186. Certainly 2 will. 186 divided by 2. I know that'll work because it's even, right? So 2 times 93. Um, let's see if 3 will. 186 divided by 3, 62. So 3 does divide it. Let's see if 4 will. Let's see. My guess is that it won't. 46.5, so that is a no. The reason I knew that is because when I took the 2 out, what was left over was odd. You would have to be able to take 2 2's out of it to let 4 divide it. I know 5 won't divide it because it doesn't have a units digit that's either 0 or 5. I'm using a divisibility test there. Let's see if 6 will divide it. It sure seems like 6 should divide it if both 2 and 3 divide it. Let's see, 186 divided by 6, I get 31. So 6 times 31. Let's see if 7 divides it. 186 divided by 7. 7 doesn't work. Let's see, 8 won't work because 2 and 4, well, because 4 doesn't. But just to check, you could check it. 186 divided by 8. No. Let's see if 9 divides it. 186 divided by 9. We get 20. No. 10 won't divide it because it doesn't end in 0. Will 11 divide it? Nothing. Will 12 divide it? Let's see. Doesn't work. And then will 13 divide it? Let's see. And it doesn't work as well. So at that point we can stop because any quotient, I don't know if you noticed this, when I divide it by 13 I got close to 14. So that means if I divide 186 divided by 14, I'll get something less than 13.5, which is the turnaround. And so all of the quotients will be in this range, and we've already searched this range, right? So what does this tell us? There are 1, 2, 3, 4, 5, 6, 7, 8 factors of 186, and they are 1, 2, 3, 6, 31, 62, 93, and 186. So there they are, an efficient way to find factors, a really large number. I mean, if you think about it, if you were to take an inefficient method for checking factors, you would check every single number from 1 to 186. And of course, this boils down to checking just 13 of them to produce the pairs, right? So quite a much more efficient way to do this, right? So hopefully that gave you a sense of how to find factors. I do want to show you really quickly that there is a nice way you can use your calculator to do this. We're used to using the y equals editor in the, I guess I'll zoom in a little bit, in the graphical interface here to put in formulas, or I guess functions that we want to know the graph of, but you could also use it to check for divisibility. Just take 186 and divide it by x. And then if you go to the table set, which is second window, you can let the table start at 0 and step by 1. And then if you go to the table, you can take a look and see, well, when I divide it by 1, I get 186. 2, I get 93. When I divide it by 3, I get 62. And then I get a decimal here and here for 4 and 5. And of course, 6 is paired with 31. And then 7 is paired with a decimal, 8 with a decimal, 9 with a decimal, 10 with a decimal, 11 with a decimal, 12 with a decimal, 13 with a decimal, and I can see once I get to 14, the quotient is now less than 13, so I can stop. So basically, this same exact table you can reproduce all at once using the simple command 186 divided by x, and the table setup and the table function of the graphical interface of your graphing calculator, if you have one. So let's do something a little bit fun since we're online. Why don't we use the number 198 and find all those factors. But what I want you to do is I want you to share your answers with the rest of the class. So this would be akin to group work in class if we were in class. So once you have a picture of all the factors of 198, would you go ahead and upload it to this advanced form here, factors of 198? Here, what I want you to do is post a picture of how you found all the factors of 198 using an efficient method. And then take a look around at others' methods. Did they find the same factors and did they use the same method? And then respond to your own solution with a response to these questions. So does it look like you're doing the right thing? Is everybody getting the same answer? So please post a quick solution to that as part of today's lectures. Let's go ahead and end on one other question I find really interesting. So here's a nice question from your author. She says this. She says, Carmina noticed that factors always seem to come in pairs. So for example, 48 can be written as 1 times 48, 2 times 24, 3 and 16, 4 and 12, 6 and 8. So the number 48 has these 10 factors that come in 5 pairs. And Carmina wants to know if every counting number always has an even number of factors. So is this what always happens, that you always get an even number of factors? So investigate her question really carefully. When does a counting number have an even number of factors and when does it not? See if you can find some sort of way to understand that. When are they an even number of factors and when are they not? And then post your solution as a one-page answer. Here again, let's just play the game again as part of lecture. So instead of this forum, I have another forum here called Carmina's Question. And again, in this forum, just take some time to investigate her question and post your response here, and then take a look at what others' responses are. And did you come to the same conclusion, or did seeing other solutions make you want to change your response? And then just respond to your own solution with a response to these questions. So hopefully you get the idea. Post your solution and then view other people's solutions and then respond to your own solution with whether or not you think you have it right or wrong. Both of these forums are called Q&A forums. So in other words, I've set the modality so that you can't see what other people have posted until you post a solution yourself. So if you're looking for a peek, you won't get it until you post your solution first. So that's about it for today. I'm done about I've done it about 27 minutes, but you should have at least 5 or 10 minutes here of posting your solutions to both of these questions. And remember that those are found in the number theory section of our course. Here's the slides, and here are the 2 forums I'm asking you to use to check your understanding of today's lecture. All right, I hope to, I will be back on Monday, and I look forward to reviewing for our first test and talking about what you can expect there on Monday. Remember, the next Wednesday is when homework, your PAT, and the first exam are all taking place. So it's a big week next week as far as assessment goes in this course. So once you've finished brushing up on factors and multiples, I would just suggest that you put some time in this weekend studying and preparing for the things that are due next week. All right. Hope you have all a great weekend, and I look forward to getting together again on Monday. See you then.